For 6.2, we're going to start off by talking about transforming random variables. It says El Dorado Community College, which is the community college by where the author lives in Arizona, considers a student to be full-time if he or she is taking between 12 and 18 units, which is like credit hours. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester has the following distribution, and we can see that here. So X is definitely a discrete random variable, right? We have these fixed categories, either you're taking 12, 13, 14, so on. The first part here asks us to calculate and interpret the mean and standard deviation of X. And what is X? That's our random variable that represents the number of units that a kid at this school is taking. And I say kid, they might be grown up, just whatever the student is at this college, right? So let's start with the mean. We've done this for discrete random variables in the past. We just take each outcome and multiply it by its probability, and then add up all of those products. So 12 times 0.25 plus 13 times 0.1 plus 14 times 0.05, and so on, which gives us our mean of 14.65 units. Apparently, that would be the average number of units for a randomly selected student at El Dorado Community College. Or another way to phrase that, the expected value of X, right? The expected number of units for a randomly selected student at this school would be 14.65 units. That's an average. Okay, and we need the mean so that we can calculate the standard deviation. So for the standard deviation, we're going to take each individual, let's start with 12, subtract the mean, square that difference, and multiply it by its probability. Then we'll take 13, subtract the mean, square that difference, multiply it by its probability. And then we get a little bit tired, so we just put ... and that's okay because we've demonstrated the pattern now, and we'll skip all the way to the last one. So it's 18 minus the mean, square that difference, multiply it by its probability. And then don't forget to square root this whole thing. All right, square root of that, and we get 2.06 units for our standard deviation. So we still need to interpret that. We can say the number of units, we should say for a randomly selected student at this college, will typically vary by 2.06 units from the mean, which was 14.65 units. Okay, so that should have been easy enough. We've had experience calculating the mean and standard deviation for other discrete random variables. The reason we start with that here is because now we're going to transform this random variable. So building on that scenario, the next part says, at El Dorado Community College, the tuition for full-time students is $50 per unit. So if T equals the tuition charge for a randomly selected full-time student, T would be equal to 50 times X, because remember, X is the number of units that a student's taking. Here's the probability distribution for T. So if you'll notice, where there used to be X's in the X row, each one of those values has been multiplied by 50. So 12 times 50, for example, became 600. And then the corresponding probabilities for each of these would be the same. Okay, so let's go through the same process to calculate the mean and the standard deviation for T, our new discrete random variable. So T basically is just the number of units times 50. So let's start with the mean of T. We'll take 600, multiply it by its probability, 650 by its probability, 700, and so on. So as long as we show the first 2 or 3 terms of the pattern, we can put ... and go all the way to the end, which gives us our mean of 732.5, or $732.50. So you might have expected that. That's actually just the old mean from X times 50. What about the standard deviation? So let's start with 600, subtract the mean, which was the 732 number, square it, multiply it by its probability. Then let's go to 650, subtract the mean, square it, multiply it by its probability. Then we get a little bit tired. That's okay. We put dot, dot, dot because we've demonstrated the pattern all the way to the last term, which is 900. And don't forget to square root this whole sum, which gives us $103 for the standard deviation. And you might notice that's just $50 times the old standard deviation for x. So what does this show? That shows that the mean of t was just 50 times our old mean for x, which was 50 times 14.65. In other words, 732.50. And then for the standard deviation, it's just 50 times the old standard deviation for x. So 50 times 2.06 gives us $103. So what does that standard deviation represent? Well, if you randomly select a student at El Dorado Community College, they'll typically be about $103 from the mean price for tuition of $732.50. So what does this prove more generally? What is the effect of multiplying or dividing a random variable by a constant? So just a constant term. So let's say our constant is just little b, right? A constant number b, whatever b is. In this case, it was 50. So if you multiply or divide by b, that'll change things like the mean. We saw the mean. It'll also change the median, the quartiles, the percentiles, and the max or the min. And the math's actually really easy behind these. You just, if in this case, if it's $50 per credit hour, you multiply everything by 50. So the mean, the median, the quartiles, you would multiply all those things by 50. And as far as measures of spread go, you would just make sure to multiply by the absolute value of b, right? Spread you can think of as a distance. So the standard deviation, the IQR, the range, all of those would be multiplied by the absolute value of b, because we can never have like a negative standard deviation or a negative IQR or a negative range. Those things are sort of a way to measure distance. So that takes care of the spread. Those are measures of spread. These are the measures of center, mean and median. Otherwise, quartiles, percentiles, max, and those are measures of just specific location. And as far as the shape goes, the shape of the distribution would remain the same, right? If you multiply every single thing in the distribution or divide every single thing in the distribution, the shape of it would actually stay the same. So if x was normal, t will also be normal. The shape will stay the same. Okay, so that's the rule for multiplying or dividing by a constant term. Let's look at the next scenario where you add or subtract a constant term. It says, in addition to tuition charges, each full-time student at El Dorado Community College is assessed student fees of $100 per semester, and that's regardless of how many classes you take. One of the harsh realities of college, you have to pay some fees, flat fees, no matter how many credit hours or, in this case, units you take. So we're going to use the letter capital C, and C is going to be equal to the overall cost for a randomly selected full-time student. So the overall cost would be your tuition, we did that in the last problem, plus everybody has to pay this $100 flat fee. So that's what this new random variable C represents. It's 100 plus T. So here's the probability distribution for C. And if you'll notice, each one of these categories was just increased by 100 for that $100 flat fee. So again, let's calculate the mean and the standard deviation. So now the overall cost is the tuition, which we did in the last problem, plus $100 for each student. So what's the mean of C? So let's start with 700, multiply it by its probability, 750 times its probability. We're going to add all these up until we get to the last one, 1,000 times its probability, which gives us our mean of 832.50. And that should look roughly familiar and something you might have guessed actually. If we add $100 to each kid, our new mean is actually increased by $100. How about the standard deviation? And this one you may or may not have guessed. If we add $100 to everybody, then does the spread of the distribution really change? So the standard deviation for C, let's start with 700, subtract our mean, which in this case is 832.50. square that difference, multiply it by its probability, which is 0.25. Then let's go to 750, subtract the mean, square that difference, multiply it by its probability, so on and so forth. Let's go down the line all the way to 1,000, subtract the mean, square it. You'll notice if you calculate this, you're still at $103. So what does that prove? If we add $100 to every single student, it takes the entire distribution and shifts it, 100 units in this case, but the spread of those points, of these data points, wouldn't change. So the standard deviation, therefore, doesn't change. So we can say for the mean, we added $100 to each kid, so the mean of t plus 100 gives us our new mean of 832.50. And then as far as the standard deviation goes, well, it's the same exact standard deviation that we got for the last problem, which was for t, the tuition. So adding $100 to each kid didn't change the spread. The spread of the distribution would still be $103 for the standard deviation. Okay, so now let's generalize this effect. So what is the effect of adding or otherwise subtracting a constant to a random variable? Okay, so for starters, let's get this out of the way. We're going to talk about shape, center, and spread. The shape stays the same. So if you add the same value to every single individual in the distribution, you just shift the entire distribution, the shape will be the same. That's unchanged. The other thing that we just showed, in this case the standard deviation, but in general, measures of spread are unchanged. And by measures of spread, we're talking about not only standard deviation, but also the range and the IQR. So that's actually a really important idea. So keep that in mind. If you're just adding or subtracting a constant to a random variable, the standard deviation, the range, the IQR, the measures of spread will not be changed whatsoever. Whereas the measures of center or the measures of location, so like the mean and the median, those are two measures of center, those will change, obviously. If you add 100, they'll shift up by 100. And also the measures of location, like percentiles, or quartiles, or max-min, all the measures of location, or if you want to call it measures of position, those all get shifted just like the measures of center, like mean or median. They'll get shifted by whatever the constant is. In this case, it was plus 100. Okay, so then what is a linear transformation? We've talked about adding or subtracting a constant. We've talked about multiplying by a constant. So now let's talk about big picture. What is a linear transformation? How does a linear transformation affect the mean and standard deviation of a random variable? So let's just start with a random variable x, and that's what we began these notes with, just a random variable, call it x. So when we transform this, when we transform x, we're going to have a new random variable when we're done. And for now, let's just call that y. And y is going to do a couple things to x. So y maybe would multiply x by a constant. We'll call that a. So a times x. And then maybe it might add or subtract a constant. And let's just call that lowercase b. So when people talk about linear transformations, hopefully you recognize this equation, right? Doesn't this sort of look like the equation for a line? Like a might be the slope, it's multiplying to x, and b might be the y-intercept, it's being added to x. And this is how we're transforming the random variable x. We might multiply it by a constant like a, and then add or subtract a constant like b. And then our rules for mean and standard deviation, we would say the mean of y, well, you simply take the mean of x, and if x is being multiplied by a, then the mean would be multiplied by a. And if b is added to x, then you would add b to the mean. So that would give you your new mean for y. You would take the old mean for x, multiply it by whatever a is, and then add on whatever b is. And then for the standard deviation of y, all we have to really worry about is the multiplying constant, a. So we proved earlier that adding or subtracting a constant doesn't influence the standard deviation, like right here. So the plus b part, that won't change the standard deviation. Okay, let's look at our scaling a test example. It says in a large introductory statistics class, the distribution of x is the raw scores on a test, which was approximately normal, with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4, ooh, that's nice, and also adding 10, that's extra nice. So he's putting a nice curve on these tests. Part A says define the random variable y to be the scaled score of a randomly selected student from this class. Find the mean and standard deviation of y. So first, let's start with the original random variable, and that's x. So it tells us x is normally distributed with a mean of 17.2 and a standard deviation of 3.8. So this is the stats notation here. You can put this little squiggly and then capital N, and that summarizes the distribution for x. It's normal with this mean and this standard deviation. So that's a nice shorthand way to illustrate that. So y actually transforms this random variable x. Apparently he multiplies their scores by 4 and then adds 10 to them. So here's our new random variable y. Now we know the shape will be the same. So if x was normal, the shape for y will also be normal. But what about the mean and the standard deviation for y? Well, as far as the mean goes, we just take the old mean for x, multiply it by 4, and then add 10 to it, which gives us 78.8. The standard deviation, you only have to worry about the multiplier. So 4 times the old standard deviation for x. So adding or subtracting a constant does not change the standard deviation for y. And again, we know the shape will still be normal, so we can say the distribution for y is approximately normal with a mean of 78.8 and a standard deviation of 15.2. So we've got our y distribution. We transformed the random variable x into this new random variable y. Part B asks, what is the probability that a randomly selected student has a scaled test score of at least 90? So this is definitely a normal distribution question. So let's start with, what's the probability that y is greater than or equal to 90? Because y represents the scaled test scores. And then we can illustrate this by sketching a normal curve, right? This is our y distribution. There's the mean right in the middle. We can give it a label, right? Mean and standard deviation. And then let's mark off 90, which is somewhere above 78.8. And then shade everything above it. That's going to represent our probability. And to find that probability, that area there, you can either go old school and try to calculate the z-score for 90 here and then look it up on the z-score chart, or if you're like me, you keep the calculator handy and you're going to use the normal CDF command. So we can say using technology, the command normal CDF. And now the lower bound, we've marked that off, that's going to be 90. The upper bound in this case would be, well, technically infinity, 1e99. And then just make sure you get the correct mean and standard deviation for the y distribution. So we've got our mean and our standard deviation, which gives us an answer of 0.231 for that area. And your calculator will actually draw that for you if you select the draw option, by the way. So what does this represent in context, that 0.231 number? That represents our probability, but in context we can say the probability that a randomly selected student scored at least a 90 is 0.231. Okay, so that's the end of these notes. To summarize, we talked about linear transformations. In particular, we talked about the effects of multiplying or dividing by a constant and what that changes, and then adding or subtracting a constant and what that changes. Just keep in mind that adding or subtracting a constant does not affect measures of spread. So the standard deviation is unchanged if you add or subtract a value to the random variable. Okay, so that's all for these notes. I'll see you in class.